Hello there. Okay, so this is chapter 1, section 2 for differential equations. So, in the previous class, video, whatever it happened to be, we talked about how differential equations are equations where you have the derivative is equal to something. And what you're solving for is the function that has its derivative as the derivative that you were given. And some people probably mentioned, like, oh, that's basically how do you find the answer? Well, you take that derivative and then you take the antiderivative to find the solution. Unfortunately, that doesn't always work, but we're going to talk about, well, sometimes it does. So let me go to writing mode. Oh no, it's not working. Not working. There we go. Cool. So the problem is that sometimes your differential equation dy dx might be equal to something which depends upon x and y. If your derivative has x and y in it, you're not going to be able to integrate and solve for what you want. You're not going to be able to just find the solution by doing the antiderivative. But if your derivative is only dependent upon x, then yes, you will be able to solve this. How will you be able to solve this? Well, you can integrate both sides. You're like, okay, let's integrate dy dx. Let's integrate it with respect to x. And let's integrate f of x with respect to x. Right? That's not going to work in this example on the left here, because on the right hand side you're going to be dependent upon y, and then you're going to have like partial derivatives. Not going to work out for you. So what happens over here? Well, these dx's cancel. You get integral dy equals integral f of x dx. So when you integrate the left-hand side, you're going to get y. When you integrate the right-hand side, you get big f of x plus c, the antiderivative, right? So that would be your general solution. How would you find a particular solution? Well, you'd have some initial value, y of x naught equals y naught. That will allow you to solve for c, right? So you can solve and you can plug that in. So like as a quick example, I could say that your problem was dy dx equals 2x plus 3, and y of 1 equals 2. Okay, so you can multiply both sides by dx. You get dy equals 2x plus 3 dx. Integrate. You get y of x is equal to x squared plus 3x plus c. You can now plug in your initial value into this, and you get y of 1 equals 2. Now if you plug that 1 in, you get 1 squared plus 3 times 1 plus c. So you get 2 equals 1 plus 3 plus c. 2 equals 4 plus c. Subtract 4 from both sides, you get c equals negative 2. So it's what would your particular solution for this initial value problem be? Your particular solution would be y of x equals x squared plus 3x minus 2. So this is your particular solution. Okay, so this is just like a 101B or even 101A simple integration problem. Okay, really easy to solve. All right, you're given your differential equation, you change things around, you can just integrate both sides, solve for your constant to find your particular solution from the initial value. Let's do a more complicated example. This will be a second order example. Okay, so remember, second order means the degree of the derivative that you're dealing with. So let's say you have second derivative of y with respect to x equals little g of x. Okay, so if you integrate your second derivative with respect to x. So integrating your second derivative will give you your first derivative. So instead of writing it as dy dx, I'm just going to write it as y prime. Integrating little g of x will give you the antiderivative big G of x plus c. Now notice this is another differential equation. It says dy dx equals g of x plus c. You can also solve this. Multiply both sides by dx, you get dy equals g of x plus c dx. And I can integrate that. The antiderivative of dy is your y of x. Now, this, you can use the properties of the antiderivative or the indefinite integral. This becomes the antiderivative of g of x with respect to x plus the antiderivative of c with respect to x. And so we can't do anything about this one. That's something. But you can find, let's call this c1 now. You can find the antiderivative of this. That's going to be c1x. And then you get another constant, which we'll call c2. So what's your function? Your general solution is whatever the antiderivative of the antiderivative was, right? The antiderivative of g of x plus c1 times x plus c2, another constant. Okay, so interestingly enough, any order equation where you have just depending upon x on the right-hand side, you can just do repeatedly integrate, and eventually you'll get your solution. Okay, awesome. Okay, so I want to talk a little now about velocity and acceleration. Okay, because these, one second, let me close the door. Because these physics problems show up a lot in, what's it called? Differential equations. So I just want to get us some common vocabulary here. Generally, x stands for your position of an object, and your position is a function of time, right? The position of the object depends upon at what time you are, because it's moving around, right? At different times, it's at different positions. Okay, so this equation here, when you take the derivative, you can turn it into a differential equation, dx dt, because remember, position is dependent upon time, so you take the derivative with respect to time. That'd be equal to f prime t. Or what's another way that you could write it? You could write it as x prime t equals f prime t. So this is now a differential equation. And you can rewrite it. The derivative of position with respect to time is called velocity. So the velocity equals f prime t. Okay. So if you have a known velocity, it's a differential equation which you could solve to find position, the position function. Let's say you take the derivative again. Well, you get the second derivative of x with respect to t. That's f double prime t. Or you can write it as x double prime t equals f double prime t. You might remember that the derivative of velocity is acceleration. So acceleration equals f double prime t. Okay, so this is a second order differential equation. This is a first order differential equation. Now notice that this second order differential equation only depends upon the independent variable t. We just found out that you could do the antiderivative or integration to then get a first order problem, which only depends upon t. And you can then do anti-differentiation or integration to find your original position function. Okay, so you can solve these. That's like why we just showed like, oh, second order differential equations, which only depend upon the independent variable, you can integrate twice and you get your solution. That's exactly what happens with these acceleration problems. You might be more familiar with looking at this a different way. So we have acceleration equals f double prime t. Let's rewrite that as acceleration equals the second derivative of x with respect to t. Now we know that the second derivative of x is the first derivative of velocity. All right, so that's a first order differential equation. The second order differential equation can be rewritten as a first order differential equation. This usually shows up in a more common form of force equals mass times acceleration. If you solve this, you're saying acceleration equals force over mass. This force over mass is that f double prime. Okay. So usually you're used to seeing it f equals ma, but when you write it as a differential equation, you usually want to say, hey, this acceleration equals force over mass. So we can solve this. Let's start off with this one right here. We can turn the second order differential equation into a first order differential equation. You can then multiply both sides by dt, so you get a dt equals dv. You can then integrate. On the right hand side you get velocity. On the left hand side you get at plus some constant. You can now rewrite this at plus some constant equals, well, the velocity is the derivative of x with respect to time. You can multiply both sides by dt, so you get acceleration times time plus c1 dt equals dx. You can now integrate. On the right hand side you now get the function that you wanted to solve for, position as a function of time, xt. On the left hand side you can integrate. You get a t squared over 2. When you integrate c1 you get c1t, and then you get your second constant, just like how we showed last time. So this is your general solution if you start off with a given acceleration. If you start off with a given acceleration, your position function will be that acceleration times time squared over 2 plus some constant times time plus some other constant. How would you find those other constants? Well, you'd have to be given initial conditions. You might be more familiar seeing this as acceleration times time squared over 2 plus the c1 is usually called the initial velocity times time, and the c2 is usually called the initial position. So for a second order differential equation, you're going to need 2 initial conditions. And we will talk about this more in the future. Right? So a first order differential equation will need 1 initial condition. A second differential order equation will need 2 initial conditions. All right, so that's chapter 1, section 2. And we're done. I'll see you in class when I see you.